So it's 2:30. Welcome to the Coroquan talk. And in fact, this is also a joint Kenzie Ontario Statistics Seminar. And today I'm very happy to introduce the speaker, Dr. Xinwei Deng. Right now, he's a professor at Virginia Tech. He is a co-director of Statistical and Artificial Intelligence Lab, SAIL. Okay. He was at Wisconsin Madison for 2 years as a visiting professor before before Virginia Tech position. And then he got PhD on Georgia Tech. And his research area is very wide, including as the title shows, interface between experimental design and machine learning, and uncertainty quantification and digital twins, the design and analysis of computer experiment. He also worked on covariance matrix estimation and high-dimensional data analysis, as well as some application of statistics in nanotechnology. And he is an AE of several journals, which I'm not going to name of them, and has published over 100 papers. And particularly, I'm very happy because my research area is a subset of his, but what he's going to talk about is exactly what I'm doing, but I'm very much sure that he's going to tell a better story. So without further ado, let's welcome Professor Deng for the talk. Yeah.
So first of all, thanks a lot for the invitations. Can you hear me? Just let me know if you have any questions. And for the online people, also thanks a lot to spend the time to come to this virtual visit, virtual talk. So it's my glad to be here. It's my second time to be in Kingston. My first time still 10 years ago in the summer. I still remember this very beautiful lake. So yesterday I came in the evening, I see the whole lake is kind of frozen or more with the snows, but still very beautiful. Just show I call the two sides about the beautiful of Kingston. So in today's talk, I like to share some of our recent work, mainly work on I call interface between this called machine learning. People nowadays talk a lot about machine learning or talk about AI, large language models. As a statistician or mathematician, sometimes we face pressure, like pressure from computer science, pressure from other domains, whether what we are doing is still useful, or we are still doing still fancy enough. So in today's talk, I call a title called New Songs for the Older Stories, right? We all know the older stories, but there's like experiment designs, but we can make this new old stories with new songs. So of course, all credit should go to all my collaborators from a different division, different university. But if there's something wrong, it's all my blame. So here's the outline. I will give a few, I call my two cents regarding data science. And if you notice my web page, I have a title called Data Science Faculty Fellow or Data Science Fellow. So sometimes I like to try to give my view, what to mean data science and how the statistics can contribute. Then talk the two ideas or in a few published work, try to say how this experiment design idea can be very useful in the machine learning, and how also machine learning idea also can be useful for the data collection for experiment design. Finally, give some summary. So here is I call 2 cents. So the first sentence is very simple. Basically try to say data science is really in the discipline, and when machine learning people talk about data science, sometimes they think about modeling, like about the modeling here. It's like how to have model, how to predict the model to be accurate or to be good. But if you talk about engineering, people they'll think about data science is more about decision making, right? So you use the data, how to improve product, okay? How to find the best tuning parameter or find the best combination about thickness, smoothness, so on and so forth. Right? So, but if you think a little bit, all these data science should come from data, right? Which I call the first pillar here. So if you think about data science, we think it's really I call in the discipline in a way from data to model to decision making, right? All come from this real world system. So from statistical perspective, we always think data are generated from certain mechanism or certain process. I call this DGP, right? DGP, not GDP, right? So GDP probably is another thing. Okay? So that's in that sense, we say towards data science, clearly it's good to be a statistician. So we are kind of good at to understand how data generated. For example, you assume normal distributions, you assume a Bernoulli distribution. That's all a kind of mechanism to assume the data generation process. But that's not exactly or not sufficient. So my second sense is say, if we understand or we agree, the way about the data science is a kind of in the discipline system from data to model to decision making, then back to data. Or then clearly we should think a little bit more, I call interface, right? Interface between how the data should be collected and how model should be doing. In other words, means when you collect data, probably you already think how you are going to the model with analysis. That's why I call the first connection. Here is interface between data collection and modeling. But meanwhile, when we do the model, for example, we do a classification model, we do a predictive models, we show, okay, the model is good, have a high R square, have low misclassification error. But think a little bit more how we should use the model, okay? How we should use this model, which means how the model should be used, that's the kind of decision making. So clearly, I mean, from a model perspective, it's also will be beneficial to integrate model and the decision making together. Model and the decision making together here. So that's what I call this decision integrated modeling and optimization. Okay? So in another sense, which means if you will think about data science, not just be statistician, right? Not just so we are good at data, good at model, but also think more about the decision making. Okay? So I know that in your department, there are many people doing a little bit on the doing more on the decision and the side. Clearly, as I say, combine all these strengths, data, model, and the decision making. That's how the data science. So the take-away message, basically, think about data science. It's a systematic thinking. It's not just one pillar, it's three pillars together. And it's good to think about this closed loop from data to model to the decision. So in today's talk, because of time limit, I will mainly focus on the first part. If I'm lucky enough, get the invitation for the third time to visit here, I will talk more about the second part. Okay. So in this piece, mainly we try to say we should think a little bit more between data collection and the machine learning or modeling. So why is this become a niche or a need to do it? Because I'm using the figure here. Oftentimes we're doing our research, work hard, but sometimes we overlook what people doing, especially what the computer science people do. Okay? So you can imagine this one looks handsome, doing A/B testing, histogram, the confidence band statistician, right? So statistician, when we are talk, what computer science band? Right? So this one look not so handsome on the computer, work so hard coding every day, right? They basically be not aware of, right? So sorry. Okay, then when they are doing, like when they talk, right? They go to the conference, machine learning conference, or this NIPS, ICML, or the kind of conference. We may not pay attention, right? We are doing our homework. Sure? So really there's a gap I've got between computer scientists or machine learning people and our statisticians, right? So clearly a better strategy we call let's work together. Let's work together. Okay. So in this talk, as I say, the first part where basically I like to elaborate a little bit using the experiment design idea. Experiment design there, I call DOE idea, really can be make machine learning more efficient. Okay. Remember, machine learning try to do the modeling, try to find the best setting, so on and so forth. So the talk is part of the recent published paper. Okay. So the problem we are interesting, essentially are interesting is kind of a data with kind of interesting structure. Okay? So interesting. We call this kind of data is more like experiment data or observational data, something we call QS factor, called quantitative and sequence. Okay? So let me use this example to demonstrate what the data looks like. So essentially, we are interested in a data which involves this factor. You can think about X variables. And this X variable, not just like the numerical values. Actually, it's involved in a sequence order, okay, in a sequence order. Actually, if you think a little bit more, such kind of data is widely open, okay, widely observed in different applications. For example, in drug discovery, supply chain, logistic, operational management. Okay? So the example I use actually come from my collaborator from the UGA involves this so-called drug discovery about this treatment. Okay? So essentially, we are interested in for these kind of drugs. So we want to have a treatment involves 3 drugs, but these drugs will be placed in a sequence order, in a sequential order. Okay? I call drug ABC, drug ABC. So for drug, just for these anti-tumor drugs, and what's response? Response is basically once you give these drugs in sequence orders, of course you hope it's helpful, it's useful. So the useful is called percentage. It's a percentage of the tumor inhibition. Of course, larger the better. But if you think like people like us, like if you have something, you take a drug, right? So you probably take one drug. For example, you take Tylenol not working, you take Motrin, right? Here is essentially we think there are 3 drugs in a sequence, place it. But if you think here, which means when you take the drug into the experiments, quantity matters. It's so-called quantitative. Okay? Quantitative. Of course, order matters. Okay? Order matters. So in my simple language, such kind of experiments I call order matters, quantity matters. Okay? So the data, for example, I snap of data like this way. So if you look, so basically it's like you put drug A, drug B, and drug C in a sequence order. Right? For example, the first round you put drug A first, then drug B second, drug C third. Of course, there's a time interval. Okay? For example, actually in the real example, you'll see, for example, like every drug is a half day. But for each drug, there's a different dosage. So clearly, as I say, if you compare the first experiment wrong and the second experiment wrong, right? The first 2 here, you find they're all the same, but quantity different. That will lead to different response. Of course, right? So dosage matters. Okay? But meanwhile, if you compare the first one, okay, and the third one, for example, first one and the third one, so you find for these 3 drugs, their dosage are the same, but all the different. Of course, all the matters here, which means also will lead the response to be different. So in other words, so for such experiments or such data, I call their quantity, dosage matters, but their order matters. So we call this is a called QS factor, quantitative sequence factor. So clearly, as I say, different dosage will affect the response. Different order will affect the response. But if you look at this, I call this variable or this factor, it's kind of semi-continuous, semi-discrete, right? Semi-discrete. And that's essentially challenge there. So what's the objective? As I say, from machine learning perspective, they say, okay, we want to build a model, right? So we want to build a model to understand the relationship between input and output. Here, input is more like this QS factor. Output is about like this percentage of incubation. But clearly, this is not trivial. It's because on the sequence order, there's so many combinations. On the dosage, there's so many possibilities. So essentially, if you think about potential input space, huge. Of course, it's here only involves 3 components. What if it involves 10 components? So every mathematician knows, right? 10 components, all the sequence order, 10 to the 10 factorial. That can be huge. So, but nevertheless, one step is we want to do the model, right? Model the relationship. But back to the real demand from experimenters, what they are interested. They want to find some kind of optimal sequence order associated with the dosage, such that can lead to like a best treatment. Right? So that's the part people in machine learning they call active learning. Okay? Active learning. They basically try to optimize this dosage and order such that they can lead to the best set. Clearly, as I say, it's a clear objective with certain challenge. So challenge, you try to say that given key component, there's so many possibilities, right? You enumerate all experiments? Sorry, we cannot do that unless we have infinite budget, right? As I say, well, no matter Canada and the US, budget limited. True, budget limited. So another, which means it requires a good modeling to model the relationship between this QS factor and the response, and also need a good strategy to quickly, efficiently find the optimal setting. So that's essentially the challenge. So what we propose essentially is I call a QS framework. Okay? So sometimes they call this global optimizations, but clearly if I use such kind of machine learning mechanism, the many experiment design idea can be proposed or can be used. So first of all, say, what's the initial, right? For example, initial, how many experiments you should run, what combination of the settings in terms of sequence combined with the dosage. Okay? So that's already actually in the paper, we have detailed illustration about the initial design. But for the time, I'm not talking all the detail in today's talk. So we need to build a model. So we call surrogate model. Second part, surrogate. Try to have a model relationship between input and output, such that it can guide us to, guide us to choose what's the next set, next set, so next experiment. And then do evaluation and iteratively, such that so-called active learning. So machine learning people always have a good name called active learning. Statistician always very humble, we call sequential design. But as you can see, the common ground between this kind of two strategies. And as you see, as I say, how do we come to initial design? How we build a surrogate model? How do we do the choosing the next ones? Is all kind of experiment design idea. Okay, so as I say, as a mathematician or statistician, we are kind of humble, but we like notations, right? So for me, it's very hard to avoid. So we do need some notation to introduce the methodology. So the notation, as I say, this kind of interesting factor called QS factor involve the sequence order. Like for K component, what's the order of place this sequence of the components? Meanwhile, associated with I call continuous quantity in this one. So I use a notation like this W. So this W essentially place a K components called CY up to CK in a sequence order that's called O part, associated with their quantity called X part. Okay? That's it's called QS factor. So an example basically shows that here, if you have this long three, then your corresponding X part is their dosage quantity part, corresponding O part is their sequence order. But do remember, since X and O are associated, you cannot just treat them separate. Okay? So objective, as I say, we have to try to do two things. One called modeling. Right? So we try to build the relationship between your QS factor, this W here, and the response. But we know, as we know, there's not clear relationship between these two. You cannot say, okay, it's a simple linear model. I say nothing you show there's a linear structures. But there's definitely a relationship. But meanwhile, we want to try to find the best optimal setting called W star. Okay, W star. Try to minimize. In general, you can maximize, but here we can say minimize this objective, the response. But one thing we do aware of that, because the model you build is have stochasticity, because data have stochasticity. So clearly here, this W is not just a deterministic function. So the objective we're writing here is not just a simple deterministic optimization. So that's why we involve this so-called active learning and the sequential design. So in the literature, actually, in the past 5 to 10 years, people start to think such kind of experiments, actually, but many on the sequence order, they call order of addition. So people propose one way to address so-called sequence order, sequence order. So what they are doing is say they just look pairwise ordering, pairwise ordering to compare every order sequence, order sequence. If their order sequence, so-called the O value, is in the opposite direction assigned as their index value, then we put -1. Otherwise, we put +1. Okay? So give one example, you can quickly realize. Suppose you have sequence order here, sequence order of here, the O equal to 1, 3, 2, right? 1, 3, 2, which means then you are trying to create, I call this additional variable, Z12, Z13, Z23, right? Z12, 1, right? So 1, 2, the 1 is more than 3, so that's 1, right? 1, 3, their order is 1 and 2. So the same sign, 1, the other negative. Okay, so introduce this. Then they transform the problem, okay, from this sequence order to this Z variable, become linear regression. So in other words, you can think a sequence order is more like a permutation. And the way they are to introduce this Z variable is more like this indicate variable for pairwise order. Okay? Then they are use Z to this regression. As I say, clearly such kind of strategy cannot be easy to extend to this QS factor because our QS factor have sequence order associated with X, okay, associated with X. And as you see here, the Z variable is for pairwise ordering, right? But the X variable is for each individual components. So clearly can be not extended. So what do we propose? We call MAGP. Okay, MAGP really is MA for mapping. Okay, mapping, and we propose this additive structure. Additive structure is because if you look at this kind of experiment, it's really the drug are added in a sequence order. It's more like additive structure. And we are using Gaussian process because the Gaussian process, there's no need to specify this linear structure. Actually, the Gaussian process generally is flexibility to quantify this nonlinear structure. So you put a few keywords together, it's mapping-based Gaussian process called MAGP. MAGP. So that's the reason why we're using, as I mentioned here, why is this MAGP. You really try to tackle a few challenges regarding this QS factor characteristics, make flexible variable model structures, and also the additive help to explain what's going on here. Okay, so in details, how this model looks like. So model looks like actually easy, like additive. The key thing here, just like looks like a linear equation, but the key thing here is, well, we really model essentially components we model as Gaussian process. Okay, Gaussian process. Okay. So for each component, essentially the Gaussian process and involve the covariance function here. So covariance function is on this equation. So any question? By the way, if you have any question, feel free just raise hand or just talk about it. So as faculty being more than 10 years, so I would say we are more and more robust in terms of different noise, like questions, singing, sleeping, whatever. So don't feel nervous if you ask any question. Okay? So what we do here is essentially say we are thinking each component as a Gaussian process here, and the Gaussian process key part is about this so-called kernel functions. Basically, it measures the dependency between any two response values. Okay? Two response values. So the correlation function here you can capture, right? As I say, measures the dependency between two response points will be related to corresponding to X input and two O input, right? Sequence and quantity. Okay? So for the quantity part, it's easy. We are using more like these Gaussian kernels, but for the sequence part, the trick, because sequence is called 1, 2, 3, 4. It has some meanings, but not exactly numerical meanings. You cannot say, okay, there's one observation with sequence 1, order 1, one observation with order 2. You cannot say, okay, they are different. It's 1 minus 2. Okay? So what we are using that's called is mapping. We call this O tilde and O tilde. Essentially, the key idea essentially is we try to mapping this sequence order into this latent variable. Okay, into the latent variable, and to avoid parameterizations of parameterization of diagonal, the up of diagonal to be 0. Okay. Okay. So by doing so, actually, we can maintain certain good properties. So one thing, as I say, is we do not worry about how the sequence order plays a role in terms of correlation functions. Instead, we are thinking the sequence order are mapping to a latent space, are captured by this coefficient. And second of all, by doing so, we can guarantee these covariance functions to be well-defined, so-called as positive semi-definite. Okay. So after that, essentially, why we adopt this Gaussian process, because we need to quantify uncertainty. And the key thing, as later you will see, this uncertainty, okay, the uncertainty for this MAGP is crucial to do this so-called active learning, because you need to quantify uncertainty such that you are able to guide the whole procedure to choosing so-called the next points, okay, next setting about the sequence order and the quantity to find what's the best combination. So the parameter estimation is not complicated. Of course, they involve quite a bit of parameters here. So essentially, we are doing this negative log likelihood optimization. Okay, so of course, we may adopt optimization strategy to enhance the computation, but in general, it's not complicated. But good thing is, by doing the Gaussian process, we can lead to I call a predictive distribution, not point estimation. on the estimation. So we have a Gaussian process, essentially the prediction follow the mean and the variance. Okay, so here are some numerical examples. As I say, such kind of things are actually very common. If you think about it, so this is a very typical example from operational research, which doing so-called single machine scheduling. The single machine scheduling is very simple. You have k tasks and arrange to a single machine, but you need a sequence order. And the different tasks have different difficulty in terms of processing time. So processing time, yeah, sequence order. So basically, we try to see whether our model have advantage. So compare, as I say, if you have 6 tasks, the sequence order is huge. It's not huge, but it's already hundreds. So we try to show our approach, so-called 2D dimension, is mapping the sequence order into 2-dimensional space, or mapping to do this full dimension space. In full dimension become this for k-1 can perform better than so-called PWO. In the paper, we have more numerical study involve different scenarios and the different applications. But here, I just mainly demonstrate the way we're doing this MAGP has some advantage in terms of this prediction. Okay, so that's the same. Then we say, as I say, why this the way we build models? Okay, we build a model. It's just one step. Final goal is we want to find the optimal setting. As I say, the purpose why we need this MAGP is because by doing this Gaussian process, we can quantify uncertainty about the prediction. It's not just say, okay, so just predict what's the response, also provide a distribution. And the distribution is crucial when we do this so-called active learning or sequential design. So as I say, it's not possible as to run all experiments because the sequence order can be possible value of x, so the space can be huge. So what we do is try to say, can we do a little bit smarter? Smart in ways, you can start with a small run size of experiments, collect a small set of data, then build models. The model should tell us which is the next data points or next design points. We try to do the things. So when I teach, I always use the example to tell my students. So you should try a few homeworks, then to know what you are good at, what you're not good at. Then you choose next homework problem, which you are not good at. You continue the process, then you become superstar. Right? So that's essentially so-called simple sequential design idea. Okay, so clearly, as I say, you cannot just directly using your prediction response. That is a distribution. Even you see the values, it's a predictive distribution. So what we want, essentially, we introduce is called improvement. Okay, improvement. So-called improvement is we hope the next data points is smaller than the current observed smallest values, such that we can continue improve. And as I mentioned here, which when we say the next point, this is a distribution. So it have a distribution. That's why this S is the density function. That's why we do integration to the extreme. So this is a well-known in this global optimization called expected improvement. And why we need a Gaussian process is because this integration sometimes cannot be very tractable or complicated. But under the process, it has a closed form. Even it looks ugly, but it's better than numerical calculations. So it have a closed form. So, but the tricky part here essentially say, okay, now we can try to find the next design point, to be the point such that maximize this expected improvement. Expected improvement. Once you have the new response, you can update the model, update the models, it gets the new data points, then you can continue until you have sufficient good performance. So, but however, such things actually is not trivial. So timing, I don't provide the detail here because when you do this search, so when we do the search, remember this W is not just a continuous values of vectors, right? It's involved both X and O. Both X, O, which means you try to search in a space half discrete. So for people come from optimization side, people say continuous optimizations, we can do this gradient. No, it's not that easy. Not that easy. And for the people from experiment design side, they say, okay, they can do this coordinate exchange or heuristic or this genetic algorithm, whatever. Okay? So, but like this problem, essentially how to efficiently solve this W do involve the combined idea, both is continuous optimization and the discrete optimization. Okay? So actually, we're also using some experiment design idea to quickly find this in the paper. But for the timing, as I say, I will overlook the details. So let's back to the case study. So this case study, as I say, we collaborate with people from U. As I say, they do this kind of drug experiments. Actually, they have these 3 drugs, okay, 3 drugs, and do apologize for my not very fluent English. So some terminology is very hard for me to pronounce. Okay? So there's 3 drugs, 3 drugs here. And for these 3 drugs, essentially they do this 24 experiments. 24 experiments. Actually, you may wondering why 24, because drugs sequence order, that means 6, 3 by 2 by 1, right? But for each drug, their dosage, they change the level for dosage for drug A and drug B, but fixed for drug C for some reasons. So, right, that means A2 possibility, drug B2 possibility, that's why there are 4. Multiple 6, that's 24. Okay? So this experiments is not cheap. They perform on these cells, and for each drug, when they place it, just wait for 6 hours. Okay? Wait for 6 hours. Okay? Then get the response and get the data. So what we do is say we have this initial design. Actually, that again, it's a very interesting topic here. It's like, how can we get the initial designs? Because this initial design is also in this half continuous, half discrete space. So we have a clever approach to have the initial design. Once the initial design, we apply our approach. Okay, our approach. Actually, you can see that after the sequential rounds up to the after 7th, we quickly can catch so-called maximum in this current 24 rounds. So basically, we try to show such approach can be better than benchmark. Okay, so-called benchmark, one naive benchmark, just randomly, right? Randomly pick. So I always tell my students, so-called random pick is your close eye. So you have a bag of Skittles, your close eye, random pick. Right? So that's why it's always good or bad. It's cheap, quick, but may not be as good. Right? The same thing, we try to compare the benchmark 2, which do this PW approach, right? Pairwise ordering approach, can show that actually PW even can be worse. Only have 40, if you like the frequency, only have a 40% to catch the maximum. Okay, so that's the first part of my talk. Any question or comments? Okay, so I will pay attention of time. I know everybody is busy, have schedules. And so my second part essentially is try to, from different angles, try to think. We always try to think, okay, as a statistician, we help computer scientists, right? So we help biologists, right? Because we are, I call data guy, data guy. So the second part actually is collaborate with people from computer science, try to show that the computer science idea also can be very helpful for data collection. So this is also we can show that the way to combine machine learning idea and experiment idea can be very powerful in this modern called AI or large language models. So this is a joint work with my former students. Now is in Amazon. So Amazon and also a lot of collaborators from different institutions. And there's based on one actually is on the machine learning conference. The other is going to be submitted. So the problem we are working on actually like this way. So again, remember this not very handsome guy, right? Very handsome. So what we realize as people in this field, we realize people like us talk about data collection, talk about experiment design. When we talk to computer science people, we found they are using different terminology, are talking the same thing or very similar. So which means we talk about the design, right? We talk about the design, they talk about the modeling, right? Machine learning. So, but they start to also talk our language, okay? Our language, our experiment design, but using different terminology. Okay, so if you talk with machine learning people, so they talk about data collection. What do they talk about? So what do they talk about? Basically say, okay, they talk how to collect data to maximize information gain. Right? Statisticians know, oh, information gain. Do you mean facial informations? We are familiar about facial information. They say just information gain, right? The gain is better. So they talk about the Bayesian optimal design. They do sometimes they say they always like Bayesian. Actually, later we'll expand a reasoning. Actually, the reasoning is very crucial from different angles regarding what means probabilistic generation from. They talk about the valuation bound. Okay, do you mean valuational inference or just the valuation? They talk about the mutual information. They talk about more neural network implicit model like not available. So we get scared. Why? No likelihood. What can we do? And we cannot do maximum likelihood. See? So that's, I think, probably is our kind of weakness or conservativeness, not so open to talk with people. They are very brave. You will see they are very brave. Okay, so motivation example. It's really try to say, if you look at experiment design problem, it's not just like choosing X, choosing O. Sometimes it's really give you a system, tell me how to weigh choosing points. Okay, so very simple. For example, you're going to collect data. Okay? Collect, for example, there's an infection disease, all this epidemiology simulation models. So what they want is very simple. Tell me at which time point to collect data. For example, time point 1, time point 2, time point 3. Suppose I just only have 3 chances to collect data. Tell me what are the best time point to collect data such that I can understand the system better. So, as I say, object very simple. Optimal time points to collect the data. Maybe it's a simulation system, okay? Maybe a real system. And what they are talking about is just find a utility functions, right? Just find a utility function, maximize the utility such that the information gain to be maximized. Okay? That's their thought. So then, as actually, if you look this kind of design literature, we do Bayesian experiment design, right? So actually, I said Bayesian, we are familiar, experiment design familiar, we put them together, still very familiar. We thought we are comfortable, but quickly we find we are not. Especially when we touch neural network, likelihood is not possible. Bayesian experiment design seems not go through, right? So essentially, here's a slide basically show for Bayesian design, we are so familiar, right? So you have a likelihood functions, right? You have a prior of betas, you have a criteria about utility or information gains. You do expectation over the posterior, you do expectation over the response, then you get the object functions to search the design. So again, if you look at this slides, we are very comfortable. If you look at the next slides, you find actually we are not so comfortable. So the Bayesian design in machine learning, they're doing very similar, but actually quite different fashion. Different fashion basically say, okay, first of all, no likelihood. What is there you have? You give me an X, I give me a Y, right? Machine learning. Give X, give you Y. Give X with Y, with some parameter beta, some beta. May not have closed model form. If you ask what's closed model form of this deep learning convolution neural network, we don't have, right? So many layers, so many nodes, do we? But you give X, they give a Y, sure, on a certain parameter. So in other words, in the modern machine learning, they don't have likelihood, okay? Don't have. Even likelihood is very implicit. Okay? So in other words, when there's no likelihood, how can you do the Bayesian design? Okay? Bayesian design. So which means, but they do assume there's a prior about the beta, but it may not be a distribution. Okay? So the keywords, if you pay a little bit attention, is in our old fashion, we cannot say old fashion. In our conventional fashion, we have a prior distribution. In their modern fashion, they call have a prior engaged with a sampling. So key thing is a sampling scheme. They only need a sampling scheme, not necessarily a distribution. Just tell me how to generate the beta. That's it. Okay? So in that fashion, what they say is we just want a utility function to call information gain that you can find the design. Okay? So the key remark I mentioned here is when the machine learning people looking at data collection they don't think the likelihood, although may not be available. They don't think about the prior distribution. Everything they think is about sampling mechanism. Okay? That's key thing. So back to this, so it functions. So what they are commonly used actually in the top machine learning conference, we found they use a lot about mutual information. Okay? Mutual information. So in this work, we try to improve this mutual information estimations with this application into experiment design. So the mutual information for people who come from information theory, as I say, the department have quite a strong expertise in the information theory. So it's not complicated. Basically, it's try to quantify this amount of information about the X, about parameter of the observation Y. Okay, about observation. So formulation showing there, showing here. Okay, so the challenge is that, as I say, for the mutual information, we don't have kind of, if there's no likelihood, okay, likelihood are not available. Estimate mutual information is not easy. It's not easy. Right? As I say, if you already have likelihood, all these things probably can be integrated or numerically evaluated. But if you don't have this, distribution likelihood, how can we estimate mutual information? So one contribution, what we do, essentially say we propose a tight estimate to estimate this mutual information, estimate the information. And as you see, the formulation here is kind of complicated. Actually complicated, come from two reasons. One, essentially, we engage two neural networks to estimate this mutual information. And the second of all is essentially we try to achieve a estimate, okay, such a kind of estimate to be kind of low bias and with low variance. And we try to compare with this a bunch of approach here, approach for this machine learning. So why we do so, as I say, because when your likelihood are not available, what you have is a sampling mechanism. Okay, sampling mechanism. So if you are sampling mechanism, everything essentially you need driven by the way you do sampling. It's the sampling. So because neural network can be very flexible, such that can approximate this kind of dependency quite nicely. So let me show a little bit of mathematics and all the some detail. Again, for the time's sake, I may not go to all the details, but really I like to share a few key ideas how this machine learning idea can be helpful. So we know actually mutual information basically is this first equation. Okay, first equation. Basically, if you look a little bit closer, it's very simple. Try to compare the ratio of so-called your model and like remember X is more like, so once you have theta and what's your distribution of Y, and compare with the marginal distribution. That's essentially show the information gain once you collect the information data. Okay? So we all know this so-called the BA bound. So the BA bound is typical valuation bound. Valuation bound. The valuation bound on say, if you don't know probability P, if you don't know the likelihood of your Y given the parameters, you can replace by Q. Okay, replace by Q. Okay? So that's very nice, very nice. But clearly, it's not practical. It's not practical in a way, say, which means when it's sharp, the Q should equal to P. It means you don't know P, the best is Q, but Q is equal to P is the best. Second of all, is the marginal distribution of Y, we don't know, right? Remember, we haven't seen, if we for the data collection perspective, unless we collect, we see the Y. So the first stage, what we do, essentially, actually, I call it's a valuational energy-based evaluation. What we do is we don't know Q is fine. We just replace Q by a neural network. Why is neural network? It can be flexible enough. It's flexible. So what we do is we don't know Q. We just try to think about the Q. The Q function here, the first equation 10 here, are replaced by a neural network, the G function here. Okay, G function. So by doing so, actually, the good thing is you can get rid of Py and have this equation 11. However, as I say, bypass this calculation margination of Py using this energy function, energy-based variations, we pay a price. Okay? A price called drifting issue. What means drifting? It's because we know, you pay attention on equation 10 here, the denominator, the expectation is respect to Y. And your network is actually a neural network of X and Y. So your neural network can be drifting with respect to a function of X. In other words, means the G function here, your G function, you can add any arbitrary function of X, does not change anything because it will be canceled out here on denominator and denominators because expectation only respect to Y. Okay? So I call a drifting issue about the G function. So in other words, means even you have flexible neural network, it's too flexible in a way you have drifting regarding the function of X. So what do we do? As I say, our solution is quite straightforward. One neural network not enough, one more, two, right? Just like for people like me, one boy is enough, and the second boy. Later you find two trouble. So here, essentially, what we are really using is to address these drifting issues. We bring another neural network, okay, another neural network. So the way we bring another neural network, essentially using this duality. Okay? This is called Fletcher-Lagrange duality. This is called FLO. So this FLO, basically, you will see, if you look actually from a mathematical point of view, it's kind of also very interesting. So we want a lower bound of this log t term, okay? Negative log t term. Remember, this log t is a parameter in terms of parameter t, right? So we introduce one more parameter or u function. So u here, okay, u here, such that it's a lower bound. So apply this, I call red part, into our previous one. Remember this in equation 11, we have this log term, right? So we replace this u, right? Remember this guy is u, right? So u is a parameter. Replace this u by another neural network. Okay. So apply neural network, that's why you have this u part, u become a neural network, g parameter neural network, such that we don't have any drifting issue. So it's more like a neural network have a drifting issues with another things such that it's more restricted or more flexible. So that's essentially the key idea. What we show is there's some good property about the lower bound, the tight, and the maximizers. For time's sake, I'm not going all the details, but the key idea is say we're using this machine learning idea, this variational bound, and we are using machine learning idea of neural network to address the drifting issue. Okay, so why this is good? This good is because, as you see, the whole thing now does not involve probability distribution to enhance this variation bound. Instead, we are using the neural networks to achieve this upper bound, a lower bound. So back to experiment design, then what we do essentially say, now what we need is, as you see, is we just like parameter theta, right? Theta, and want to measure the mutual information between your parameter and the response. The larger, the better, okay? Such that we find the design. Meanwhile, we do this optimization of neural network using neural network such that make your bound as tight as to the mutual information, Okay, so there's some toy example back to the linear regression. The only thing here now, the error term is not normal distributions. It can be very complicated, such that we cannot easily have the likelihood functions. We basically try to show that the way we are doing this mutual information actually can be quite nice in terms of closer to the large, to be large, also have small variation. So we also try to extend such kind of experiment design using this so-called mutual information bound into this amortized Bayesian design, Bayesian sequential design. So for people like as old as me, maybe amortized, you know well when you pay mortgage. So the key idea basically is say, in many applications, we cannot say we do sequential design, then update the model, then continuous. Oftentimes, in the beginning, we already designed this like a sequential strategy, So what we do essentially is involve something called policy net. Okay, policy net. It's more like neural network involve this kind of time series stuff. So what we do essentially, as I say, you can have this neural network such that every time when the new response comes in, you can automatically update those and continue the search. Okay. And in the detail, as I say, we can use our mutual information bound, okay, mutual information bound, but the way we just do this initialization, continue this sequential, okay, continue this sequential. Optimize, I call the neural network parameters and the initial designs to maximize the mutual information between the response and the parameter responsibility. Okay, so this one application. So first application is back to this epidemiology simulations. As I say, in this SIR model, this called suspectable infection and recovery models, there's no likelihood explicitly. Okay? No explicit likelihood. What we really have essentially just a simulation process. So what we can do, we can find like a best design points to collect the data. So I use a delta, is the time gap. So we can show basically the way this high mutual information also is try to capture the peak and the trend there. Okay, trends. Okay, so for the time's sake, as I say, I will briefly talk the last application. So this last application is really trying to think, if you think about the design, like you're choosing data points can be non-numerical. Okay, so essentially we apply this idea of mutual information and the sequential design into this I call the smart or intelligent conversation system. So what the problem we are addressing? Actually very simple. So you ask a question, you get the answer. You ask a question, you get the answer. The question you ask is your design point. The answer you get is your response. So while you ask question, you want to get knowledge. Knowledge is your parameter theta. So in other words, means can we build a system such that we can ask smart questions? So that's essentially a design point. For example, you think a movie like Avita, right? So you can ask, for example, just like you can ask, okay, so search movie, right? You can ask who the directors, what kind of plot you are looking for, right? So such that you can quickly get the, I call the knowledge about the movie. Or you can ask a little bit dumb question, right? So for example, is it scary? The answer can be say no. Do you like it? You say yes, right? So clearly, if you think about the system as information, we should write questions. Back to experiment design, basically say we should collect good data points. So such things essentially is not trivial. In a way, say to ask smart questions, right? Smart questions. That's design problem. We not ask 10 questions in one time. We ask a question sequentially, right? Ask question, get answer sequentially. That's become sequential design. And we also need the deductive and compositional reasoning. Okay? Reasoning. So if you think about this binary tree, decision tree, if you ask a question, no, yes and no, yes and no, that can be 2 to the power in terms of number of questions you ask, in terms of potential answer. So clearly, that's not doable. Okay? So instead, we can use mutual information to measure the information gain you obtained by through the asked question. As I say, question is your X, answer is Y, knowledge about the theta. Okay? And because of neural network and this deep learning stuff, we are able to quantify the answer and the parameter. It's all text, but that's fine. We have larger language models, right? So that's essentially our strategy. So in general, we can show that the accuracy really depends on the mutual information between answer, okay, the answer, the Y, and the item of knowledge. So we build a system, actually my student built a system to show such that we call ARQ can be better to acquire information through the mutual information, through this FLO to have a good bond between the parameters and response. So we demonstrate some actually numerical examples on real data such that the way we are doing is better than this so-called reinforcement learning. So that's my last slide. So again, as I say in this talk, I share a few works such that you can use machine learning to experiment design, much cool, much fancy, much appealing. But we also can use experiment design to make machine learning much more efficient, much more reliable, much more trustable. So my last slide basically try to say we all have data, right? Older people, young people, construction all have people, and we are data Superman and Superwoman. Thank you.
Okay, before I forget, I have to do one thing. That is acknowledge the sponsorship by Kenzie Ontario. So that's sponsored by the Korean talk, and the seminar is sponsored by Deng, as well as our department. So, and do you have any question? Are there any question online? Okay. Yes, Paul.
Oh, very good point. So far our model, let's come back to. Yeah, so far, if you look at the model structure, we have these additive structures. So this additive structure, this each additive component corresponding to each drug at which orders. So in such fashion, we are able to do some sensitivity analysis or inference on to evaluate which drug, their order and the quantity are more important. So we do so back to your question, we don't have exactly try to have exactly knowledge to see, for example, what combination of sequence order is best. It's kind of more effective or kind of things. We only, because the active learning part only have a point estimation solution. We don't have uncertainty part yet. Yeah, but another thing probably you may be aware of. So far, we also try to say for the sequence order, you place the drug in the equal time intervals. Actually, like waiting for 6 hours, then you put the second drug. Wait the 6 hours, put the third drug. Then wait 6 hours, collect the response. So clearly, this waiting time or time gap also matters. And in such fashions, actually in our ongoing work, so the current work or current framework is very hard to incorporate. It's like time, also another dimension of X, right? So, and then in the ongoing work, we have a better strategy using this permutation idea or generalized permutation matrix idea to incorporate like a multi-dimension of X. Thanks.
Okay. Oh, that's not research related question, so that's okay. Last one? No? Okay. Let's go upstairs for the reception and thank you, the speaker again.